Hello, welcome to another module in this massive open online course. So, in this module, let us look at an interesting application of the principles of linear algebra in the context of machine learning, and this is a very important application termed as SVM, which stands for support vector machines, which is which can say is a very important classifier or a concept in the context of machine learning. So, let us understand this. So, what we want to explore today is this very important classifier termed as a support vector machine, very important. So, naturally this is a very important, so the abbreviation is SVM. This is a very important application in the context of ML, that is, as you are already familiar, that is machine learning. Okay. Now, what is a support vector machine? What is the principle of support vector machine? Let us try to understand this. A support vector machine does the following job. It is a binary classifier, right. So, you have, if you recall what is a classifier, you have two classes of data, you are partitioning it into two classes. So, you have data which is to be partitioned into, so this is your class 0, let us say, and this is your class 1. I can denote this by +1, by -1. We will look at more at this later, and so this is basically a partition, right. So, you are partitioning your data into two classes, and this is also, or you are basically classify, this is also basically a binary classification, right. You are classifying your data into two types, class 0 and class 1. So, there is a large amount of data that is available, and you are performing classification in particular binary, because you are classifying it into two classes, 0 and 1. Okay. So, this is essentially, we can also term this as a binary classification problem. Can also term this as a binary classification. This is 0 and 1, binary because there are essentially two classes. So, this is a binary classification problem. For instance, example, let us take this for instance, where does this binary classification arise? For instance, let us say you have a medical detection here. For instance, let us take a look at a medical example. In the medical profession, you have, for instance, the detection of presence or absence of a particular ailment. So, you have a large amount of data, let us say in terms of blood tests or X-rays or CT scans or so on, and from this data you want to classify it into two types, essentially, as either an ailment is present or an underlying disease is present, or an ailment or essentially an underlying disease is absent. So, that is a very important problem, a classification problem in the context, and problem in the context of medicine. And as you can see, that is a very important problem, because it has a lot of applications, and the answer and the response to this problem will be a yes or no, right. Is the ailment present or not? So, it is binary, right, 0 or 1, right. It is not a, what I mean to say is, you have to distinguish it from a continuous from a regression problem where the output value is continuous, that is, it can take any particular value on the set of real numbers or complex and so on, in a binary classification problem, the output has to be belong to a particular set of discrete values. In particular, for binary classification, it has to be either 0 or 1, that is the output response can either be only, it cannot be for instance 1.5 or minus 2.3, right. You simply want to know if the ailment is present or absent. Okay. A similar another interesting example, for instance in the context of quality control, and this is very important in manufacturing again. For instance, another example in the context of quality control, for instance if the manufactured object, right, if manufactured object to check to or to determine manufactured object meets the desired quality to check if the manufactured object meets the desired quality standards. For instance, you might fabricate a new car or manufacture a new car. How do you determine if this car passes all the, if this car meets the particular standard that has to be ensured by that company? You probably run a lot of tests, acquire a lot of data, put this data through an algorithm, and the algorithm outputs a value 0 or 1. 0 means probably acceptable or 1 means it is not acceptable. Now, you can see this 0 and 1 itself by themselves do not mean anything, right. These are basically what you assign. So, 0 either, so 0 and 1 can either mean, depending on what you assign, can either mean that it meets a certain set of criteria or it does not. So, 1 will automatically meet, so if 0 denotes certain aspect, 1 obviously means the opposite of that, the absence of that aspect. For instance, if 0 is the presence of disease, 1 would mean then the absence of disease, and so on and so on. Okay. The point is, now there are many classifiers that can be designed. In particular, we are going to be interested in the linear class of classifiers, because these are, we are interested in linear classifiers because these are easy to determine and easy to analyze. So, non-linear are typically much more intractable, easy to determine, and more importantly also easy to analyze. So, this is the linear classifier, and the linear classifier, the linear classification can be achieved by what is known as a hyperplane. The linear classifier can be achieved by what is known as a hyperplane. What do we mean by a hyperplane? A hyperplane is essentially a plane. What is a hyperplane? A hyperplane is actually a plane in n dimensions. That is, if I look in n dimensional space, right. If I ask the question, what is a general, that is extension of this generalization of the notion of a plane to n dimensional space, that is a hyperplane, and the expression, right, of the hyperplane is given as, it is characterized by, if you have an n dimensional hyperplane, a1 x1 plus a2 x2 plus so on an xn plus b equal to 0, which implies, now writing it using our principles of linear algebra, writing in terms of vectors. Remember, that is what linear algebra is about, developing compact notation, representing it efficiently and analyzing it. So, I can write it as a1 a2 an b1 x1 x2 xn plus b equal to 0. This you can call this as your A transpose, this is the vector x bar. So, you can write this as A bar transpose. So, this can be written as A bar transpose x bar plus b equal to 0. So, the expression for the hyperplane in n dimensions is given by a vector A bar. This is essentially a weight vector comprising of the weights a1, a2, an, then the vector of variables x1, x2, xn, A bar transpose x bar plus b equal to 0. So, I can write this as you have A bar, which is essentially your weight vector. I can call this as my weight vector or coefficient vector, and I have x bar which is equal to x1, x2, xn. This is my variable vector, right, and therefore, and b is nothing but a constant. So, I can write this as A bar transpose x bar plus b equal to 0. This is a constant, this is your n cross n1 variable vector, n cross 1 coefficient vector or weight vector, and so on. And for instance, now if n is equal to 2 implies this becomes a line, right. For n equal to 2, this becomes a line in 2D space, right. In 2D we are well aware that, so you have, for instance, let us take a simple example, 2x1 plus 3x2 plus 8 equal to 0. This is a line in 2D. Now, n equal to 3 implies this is our regular plane, what we know as simply a plane in 3D. You might have learned this in your high schools. For instance, you have 4x1 minus 5x2 minus 3x3 plus 9 equal to 0. So, this is simply what you have very much learnt earlier. This is a plane in the 3D, in the regular 3 dimensional space, and so on and so forth. And the generalization of this to n dimensional space is a hyperplane, right. So, the generalization of this of plane or concept of plane to n dimensional space is nothing but your hyperplane. This is basically the generalization of the concept of plane to n dimensional space, that is essentially to a hyperplane. And what you will see very interestingly, it is not very difficult to see, is that whenever you have this hyperplane, that is arbitrary n dimensional space, you can visualize this for now in 3D, in 2D, A bar transpose x bar plus b equal to 0. Now, it divides this into two regions. Each hyperplane divides the space, right, hyperplane. So, this hyperplane, so not just this hyperplane, any hyperplane, right. So, hyperplane divides space into two regions, right. So, this corresponds to the region, let us say A bar transpose x bar plus b greater than equal to 0, then immediately the opposite one will be A bar transpose x bar plus b less than equal to 0. And this is of course your hyperplane, that is A bar transpose x bar plus b equal to 0. So, these two, so the hyperplane divides the n dimensional space into two regions. Each of these regions is known as a half space. So, it is like taking a knife and slicing it, the object, into two parts. One is which lies to one side and other which lies to another side. One is basically characterized by A bar transpose x bar plus b greater than equal to 0. The other one is A bar transpose x bar plus b less than equal to 0. Each of these regions is known as a half space. So, these two regions, these are known as, basically these regions each is known as a half space. So, hyperplane divides the ND space into two half spaces. Okay. So, hyperplane, so we have the hyperplane divides the space what is the first half space? That is your A bar transpose x bar plus b greater than equal to 0, and the other one is A bar transpose x bar plus b less than equal to 0. And now you can see I can use this for classification. I can use this hyperplane now to separate my data such that the data belonging to class 0 lies in one half space, data belonging to class 1 lies in the other half space. That is the idea of the support vector machine. So, what is the idea of a support vector machine? The idea of the support vector machine is the following thing, that is, if you look at it, you have the hyperplane, that is, how do you find the hyperplane such that this is your data so each of these lies in its own half space. Right. So, we design a hyperplane such that partition the data into two different half spaces. That is essentially the idea behind a support vector machine. Support vector machine is to design essentially a hyperplane that optimally partitions, and we are going to look more at that, how to optimally partition the data into two different half spaces. So, hyperplane. So, what is SVM doing? Support vector machine design hyperplane to partition data into two the data into two different half spaces. That is essentially what the hyperplane is doing. the half spaces corresponding to A bar transpose X bar plus B less than equal to 0, A bar transpose X bar plus B greater than equal to 0. Okay. Now, let us formulate the problem for this. What is the specific problem? How do we do this? Problem, which means problem for binary classification. Problem for binary classification. Let us say we have, consider the points we consider the points we have m points, and this is our training set, and we have the corresponding classes for these m points. Sorry, this is not y bar 1, but these are just zeros and 1. So, these will be the scalar quantities. So, these are your, this is your training data. Again, you can think of this as the responses, similar to regression problem. You can think of this as the responses, output variables, etc. These are essentially your explanatory data, explanatory variables, regression variables, so on, or regressors. These are essentially your explanatory variables, and each yi, each of these yi, you can see, right, each yi belongs to this set. Either we can call this as not exactly 0 or 1, we will call this as -1 or +1. That is, we denote the classes as, let us say, class 0. We are going to see this is going to have a very big use. Class 0 yi equal to -1, class 1 yi equal to, or let us say yi equal to +1 for class 0. It does not really matter as long as you are consistent with the notation. So, class 0 we are saying yi equal to +1, that is the response corresponding to class 0. If the class 0 response has to be +1, if the class is 1, the response has to be, response is -1. Okay. Now, let us take a look at it. Therefore, now if we look at this, right, let us say we have our hyperplane, this is our hyperplane, and this is our A bar transpose X bar plus B. This is, let us say, A bar transpose plus B greater than equal to 0, and this is, let us say, A bar transpose X bar plus B less than equal to 0. So, this is essentially your class, let us say this is your class 1 and this is your, let us say, your class 0. Now, what you can say is that for all points, that is x bar k, right, for x bar k belonging to class 0, we must have A bar transpose x bar k plus B greater than equal to 0, which also implies I can now multiply this by yk times A x bar k plus B greater than equal to 0. Okay. So, this is for all points of class 0. So, yk you can also call this as the class label or class response or class label, you can also call this as the class label or class response or whatever it is, right. Okay. Now, similarly for all x bar k element of class one, we have a bar transpose x bar k plus b less than equal to 0. Now, again once you bring y k into the picture, remember here y k equal to 1 for class y k equal to plus 1 for class 0, here y k equal to minus 1. So, once again this means since you are multiplying by a negative quantity, you will have y k into a bar transpose x k plus b greater than equal to 0. Why? Inequality reverses. Why? And this is important. Look here, inequality reverses. The inequality why? Because y k equals minus 1. So, that is the thing. So, therefore, the same equation y k into a bar transpose x bar k plus b greater than equal to 0 can be used to represent both the classes, right, because y k equal to plus 1 for class 0, y k equal to minus 1 for class 1, and that essentially captures both the half spaces. So, for both classes the combined equation combined constraint is y k into a bar transpose x bar k plus b greater than or equal to 0, right, where we have seen y k equal to minus 1 for class 0 or y k equal to 1 plus 1 for class 0, y k equal to minus 1 for class 1. Okay. Now, the point is, now if you look at even this problem, there is a problem. What is the problem here? The problem is the following. Please look at y bar k plus a bar transpose x k plus b greater than equal to 0. Now, look at this. This is satisfied for the trivial solution a bar equal to 0, b equal to 0. Therefore, we cannot have this, we will have to tweak this a little bit, right, because otherwise if you simply say greater than equal to 0, I can simply set a bar equal to 0, vector a bar equal to 0, b equal to 0, then this is always equal to 0. So, it trivially satisfies this. So, to avoid that, we just have to tweak it a little bit, and what we are going to say is that y k into a bar transpose x k plus b greater than or equal to 1. So, we will introduce this constant 1 rather than 0. This is to avoid the trivial solution. What is the trivial solution? A bar equal to 0, b equal to 0. So, avoid the trivial solution, we will tweak this a little bit. So, now we have the two hyperplanes. What are the two hyperplanes? We have the two hyperplanes. So, for y k equal to plus 1, that is class 0, this implies, what does this imply? A bar transpose x bar k plus b greater than equal to 1. Now, for y k equal to minus 1, class 1, this implies A bar transpose x bar k plus b less than or equal to minus 1. So, if you see now, what happens to this is you essentially have now these two hyperplanes. Okay. So, now you do not have one, but you essentially have two hyperplanes. So, you can say this is your A bar transpose x bar plus b equal to plus 1, and this is your A bar transpose x bar plus b equal to minus 1. So, you have these two hyperplanes, and now what you are doing is so you have these different classes now. Let us say you have this class 0 and you have the class 1, and now you are not just fitting a hyperplane, but you are separating. So, this is the separation. So, you are maximizing this separation, or in other words you are fitting a slab. This is essentially known as so you are essentially fitting not just hyperplane, but you are inserting a slab, right, a thick partition. Like hyperplane, you can think of it as a thin partition between these two classes, right, and that such a classifier or a machine is always going to be very fragile. You can see just like a thin cloth partition between the two classes, easily broken, right. Now, what you are doing is not inserting a thin partition, but a thick slab, right, like think of this as a concrete slab, such that you want to very rigidly partition these two into two different classes, so that there is no chance of confusion or overlap, and therefore, the thicker the slab, the more robust is your classifier, the less is your chance of error, and therefore, you want to design your classifier in such a way such that the width of the classifier, the width of this slab, width of this partition is maximized. That is the idea essentially in your support vector machine. So, what is the central idea in your support vector machine? So, this I call this as the width of the slab. Okay. So, what is the aim of SVM? Now, let us look at the aim of SVM. Design the slab, right, design slab with maximum width. This implies robust classification, or this implies you have a robust classifier, implies least error. We are talking about classification error. So, the more thicker your slab, the better is your classifier, more robust, the more robust is your classifier, the lower is your classification error. Alright. So, that is essentially the idea behind support vector machine. And how do we actually design the support vector machine? That is something that I would like to next module. So, please go through this. I try to understand this concept at this level, and then we will look in detail at the workings of a support vector machine in the next module. Thank you very much.